So now we are in the topic of real numbers. Okay, what are real numbers? Real numbers are numbers that can have fractions. Okay, so how do you represent fractions in binary? Okay, so fractions are common. Okay, for example, you have 0.25, you have pi, and so on. So these numbers require special consideration. Three different representations are most popular. First is fixed point, okay, and then the format is plus minus I dot f, and this is okay for simple and sufficient for simple applications. And then we have a more powerful representation, the floating point representation, and we have formats slightly different. We have mantissa times base raised to the power e. Okay, so floating point is a wide number range and requires complex hardware if we are going to do it in hardware. And lastly, we also have what's called the rational number, where a number is written as two integer numbers. It's always a ratio, p over q. So if I want to even write the number 1, so I have to give two numbers, 1 and 1. So that's number 1. If I want to write 10, so it will be 10 and 1, because the denominator must always be specified. If I want to write pi, also can. Okay, pi, maybe you can say, okay, 22 and 7. So that will be pi for you. This will be accurate to like 3.14 lah, 3 digits. But if your register is bigger, then maybe you write pi in the more accurate way 355 by 113, if I'm not mistaken. So this is accurate to more digits lah. I think up to 7 digits. Okay. Up to here. It's accurate up to 7 digits. Really, this one pi can go to 26536. But it's accurate up to here only. But it's good enough for many applications. So this is a rational number lah. So if you want to write pi, you don't have to do. You have to find the closest number. You write them as a ratio of two numbers. Anyway, the rational number is less common, and we don't see them used in computers, except in maybe FPGA. Okay, so the fixed point format has a name called the Q format. Okay, so it's a Q format. It's a number format for fixed point numbers, written as qm.n or just qn. And m is the number of integer bits, and is optional. Okay, so when you see q and a number only without the dot, it's only the fraction part. So you can have qmn or qn only. So if qn is only the fraction with no integer, and the total number of bits is the sign bit plus the integer bit plus the n bit. And these are some examples in the Q format. Okay, so for example, I have Q 7.0. So I have 7 bits integer, all in integer, no fraction. So I have 7.0. So this one I cannot write as Q7. I must write Q7.0. And then we can have Q 6.1. So 6 bit integer, 1 bit fraction. So now the range, instead of minus 128 to plus 127, becomes plus 64 to plus 63.5. Okay, basically, these numbers divided by 2 lah. All right, and then we can have also Q3.4, 3 bits integer, 4 bits fraction, and Q7 or Q0.7. Okay, where when we say Q7, that means there's 7 bits of fraction. So all the bits of fraction, only one is 9 bit. So in this case, we can have minus 1 up to 0.99. So we cannot get to plus 1. Okay, there's no way to get plus 1. It's just like here. In the first number, we cannot get plus 128. Same here. So if you do the calculation, actually this number is 127 divided by 128. So this one is 128 by, actually minus 128 divided by 128, you get 1. this number is plus 157 divided by 138. So that's the highest you can go with Q7. And so we have actually two different formats. Okay, so these numbers are normally manipulated as regular binary numbers, but the problem is there's two conflicting notations. One is the sign bit is not counted, and we are using this because this is why I use this, because me and Dr. Osman, we are DSP people. Okay, and most of the books in DSP, they use this format. Okay? But the non-DSP people, they prefer the second one, where the sign bit is counted as integer. So if it's 8-bit integer, then in the second way is written as Q8. Okay? So this number actually can be Q8, Q7.1, Q4.4, and bottom one still Q1.7 or Q7. So this is like funny lah. Q1.7 is equal to 7. So that is if we use the second format. So the non-DSP people, they use this, and if you look for information on Q format, you find both of them. So none of them is wrong. Both of them are correct. So just to tell you ahead lah, if you go and find information for yourself, you will get confused. So to avoid the confusion, the total number of bits must be specified. So like this case just now, Q7.1 or Q6.1, we do not know. Okay, so Q7.1, Q6.1, or how many bits? So we have to know. We have to tell that both for both we are using 8 bits total. So choosing the position of the binary point depends on the largest number needed for the algorithm and also the tolerable error. Okay, so if you are doing simple ADC, you may only need 8 bits. Okay, but if you are doing high quality audio, for example, you're recording sound at CD quality, you need 16 bits. But there are also applications that need more than that. So, for example, if you are using the ADC, okay, your microphone is trying to listen to very soft sounds, so you need more bits than that. So you may even go to, instead of Q8 or Q7, you go to Q15 and go up to Q24, somewhere there. Okay, so to demonstrate how to calculate, you can see here Q3.4. Okay, so the sign bit is not part of the number here, so that's why Q3.4. There's 3 bits here, 4 bits on the fraction part. So on the fraction part, the processing is different. Okay, so the integer part is just like normal integer. Okay, so these numbers here, you can see the weighting is just like binary. 2 power 0 up to 2 power 1 and 2 power 2, and then for the sign bit we put a minus in front. Okay, always a minus on the sign bit because all the Q format are complementary. And on the right side, on the fraction side, it's always negative power. Okay, so the number gets smaller and smaller. And if you convert this to decimal number, you will not be nice, okay, because there's always 5 at the back, and then the number, they're all funny looking. So if you try to get fraction that is nice, you will always get a binary pattern that is not nice. For example, I want to convert 0.2 in decimal to fraction. The number will not be a nice pattern in binary. It will be a random mixture of 1 and 0. But if it's 0.25, or because it matches one of these, okay, so 0.25 in decimal will be 0.01. So the way we do this is this bit has weight of half, this bit is weight of quarter. 0.01, then it becomes. And more examples. Okay, this is a mixture. Okay, so some bits on the left. This one is easy because it's 101 in binary. You can convert this to 5. Okay, 4 plus 1 or 5. But on the right side, then you have to do some calculation because our brain is not tuned to do this. So the first one is 0.5, the second one is 0.25, and you add them up, we get 5.75. So normally we divide lah, right? Because each one is 1.5 plus 4. And when you do the calculation, then only you get 0.5 and 0.25. And what is the biggest number in 8 bits fraction? This is the one. So you add all these numbers, and when you go to decimal, a lot of funny numbers lah. So I don't share here. But so if you write in fraction, it will be 1/2, 1/4, 16, 64. Okay, add all this up, you get 127 divided by 128. And in decimal, it's 0.99 something. Okay, so that's the biggest number in the biggest positive number in Q7 fraction format. Okay, so what happens when you multiply? Okay, when you have numbers, you can add or you can multiply. So addition in Q format is straightforward, but when you multiply, you actually get a bigger number. Okay? The reason is this number is Q7, but in hardware it's actually 40 hex. Okay, which is 40 hexadecimal. This one is 60 hexadecimal. Okay, so the multiplier doesn't care. Okay, if you consider this number 40 times 60, it will produce 1800 hex in hex. So if you are talking about signed number or unsigned number, doesn't matter because the sign bits are all 0. Okay, if you multiply these two and if you convert that to decimal, it's actually 64 times 96, and you get 6144. Okay, so relatively small times relatively small become a big number. But if you're talking fraction, this number you cannot take as it is. Okay, you have to know which part you're going to keep. So if you're talking Q7 and you multiply these numbers, in Q7 the binary point is here, and if you when you multiply, the binary point actually shifted. It's actually shifted. So when you are going to keep the result, you're not going to keep the bottom part, but you keep the top part minus 1. So the one that is dashed in red is the number that you keep. So in this case, we have 0.5. Okay, this number is 0.5 into 7, 0.75. And if you want to get the correct number, which is 0.5 times 0.75 equal to 0.375. If you want to keep 375, you have to do this. You must take bit 14 down to 7 to get the correct value. So that's how it is. Right? And then of course, if you have one here and one here, some other place, then you have ones all over the place, and if you keep only the top part, you will remove the bottom part. In this case, is an easy example. The lower bits are all zeros, so you can remove them. But if you have ones, some of the other bits, you will have ones also at the lower numbers. Okay, lower bit positions. So those numbers are going to be dropped out. So your number will be not as accurate as before because there will be an error because you're only keeping the top 8 bits. Okay, and any questions so far? Has anybody used this before? anybody asleep?
Everything is all right here.
Okay, so never use it as expected lah. Okay, so in where can we find this semester when you are going to use your CNN when you use CMSIS? Okay, this number is used in CMSIS, and you can specify Q7 or Q15. And in the notes, I have it somewhere at the back lah, in SIMD. When you look at the advanced features of the ARM, there's the SIMD or the neon part. Then you can specify the number format Q7 in C. But it's only for when you are using that particular CMSIS library. Okay, next is the floating point number. Yeah, go ahead.
Just wondering if do we need to know how to do the multiplication through the do we need to know how to do the multiplication manually?
Yeah, this one is the basic.
Can you get us on how to do it? Because I think I forgot to do it already.
Oh, you want to review this?
Yes.
Okay. So which one exactly you want to review?
I mean, how to do the multiplication, right? How can I get the 0.011 from the 0.1 times 0.11?
Okay. First, you have to understand this number 0. is actually 0.1. Okay, that's the first thing, and then this is 0.11, right?
Okay.
Okay. This one clear?
Yeah.
Okay. then you multiply first lah. Okay. So if you multiply 0.1 times 0.11, this is the number that you expect. Right? You punch it in your calculator. Okay. So you know that this is the number that you want. So if I will write this in Q7, I will get 0, 1, 0, 0, 0, 0, 0, 0, like that. This one in Q7 also like that. But this number I will get 0, 0, 1, 1, 0, 0, 0, 0. So I know ahead of time, if I multiply this times this, I will get this. But the hardware doesn't behave like you expect, because the hardware does things in integer. Correct?
Yes.
So hardware integer hardware, what they will do is they will multiply this number 40, which is this one lah, this number. In hardware, it will do this 40, and then times 60, I will get 1800 hexadecimal. So 64 times 96, I will get 6144. So actually, if you convert this, you will get 6144 lah. If you take this whole 16-bit number, 1800 hexadecimal. Just to check lah, just to check, 1800, I will multiply to get the hexadecimal. I will multiply this column by 1, this column by 16, this column by 256, in this column by 4096 hexadecimal. So for is it 4096? 40. Let me use the calculator first. 2 power 12. 2 power 12 is 4096, yes. And then 1. Okay. So this number is actually if I'm talking, or I can just choose binary lah. There was only 2 bits here lah. Don't go fancy. So here, this is column 9, 10, 11, 12. So 2 power 12 plus 2 power 11. Use Google. I can add 2 power 12 plus 2 power 11. Google calculator, I will get 6144. Okay, so this one takes out. This is correct. 6144. Okay, so how does 6144 for 1800 get back to this number? Uh, that's that's the key lah. Okay. This is the whole this is the pattern that you get 1800 hex, but I want only this number. So to do that, you need to understand that when you do Q7, the sign bit, the green one here, is going to be multiplied by 2, okay? Or will be duplicated. The sign bit is duplicated. So one bit here, one bit here. When you multiply, the sign bit is going to be 2 here, but you're only going to keep 1. So if you understand that, then you only need to keep the 7 bits after the sign bit. Here, 1 sign bit and then 7 after this. Okay, 1 sign bit and 7 after this. So you know this is the sign bit that you want, and then you only keep 7 after that. That's one way of looking at it. Did I make you more confused?
If today the sign bit is like 1, the sign bit is 1 times 0, so it will return to
1 times 0 will be 0 lah.
okay.
You can experiment lah. If it's 1 negative and 1 negative, sorry, 1 negative, 1 positive, you should get negative lah. If one is 1, the other one is 0, you should get 1. You can try. Let me see. Can I get that? This is this one is let's say you multiply 1100, right? This is negative. Let's change only this. Okay. So what's this value now? It's no longer 0.1. What's the value now? Okay, this one is still 0.75. Okay, what's the value? 1100, 0000. Takes a long time to calculate. Huh? Okay, this one is 0.5. This one is minus 1. Okay, minus 1. Minus 1 plus 0.5 becomes minus 0.5.
Minus 0.5.
Yeah, you multiply that. So go to Google calculator for a while. Okay, 0.5. Sorry, 0.5 times 0.75. I should get 0.375. I will get negative 0.375. So okay, this is the number that we expect. So if I multiply this, the integer number will be the integer will not be will no longer be 60, but 40 will be, what's the number now? If 1100, I will get 128 plus 64. So I get 192. So I get 192 times 96. 192 times 96. Do you understand where I get this? Okay. This number, okay, 0.5. Let's see, can I delete this? I get 0.5. In Q format, it will be 1100. But this is also like 192.
没有，我现在停着课啊。
1 0 1 0 1 0 0 0 0 okay, 1696. So you multiply this 192 times 96, you will get 18432. Okay, so 18432. So 18432, how does it look in decimal? Okay, so this one I will get, wow. I'm using Google Calculator, so I will paste here. This one. 0 4 times, and then 4 times again. Sure I don't miss anything. Okay. 0, 0, 1, 0. Okay. And here, 1, 2, 3, 4, 1, 2, 3, 4 up to here. One here, up here. And 1, 0, 0. Okay, 1, 0, 0. Sorry about that. Go to display mode again. Okay. Yeah. Full screen mode. Okay, so I will get this number lah. Okay. So this one, 1192 times 96, I will get 0, 1, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. If I want to keep, so that when I keep this one, 0, the 0 in front, I will remove. Keep this, keep this. 4 bits. Okay, so let's try check this one. Okay, this one is -1, and this one is 1/2, 1/4, 1/8. So -1 plus 1/8. Do you get it? I think I missed something lah. I think I'm not getting it. But I get something, some negative number. I think I get 0.875. I'm expecting 0.275. I missed by 0.5. 0.5 is missing somewhere. Do it all over again. That's how it's supposed to be done. I'm expecting 2 at the left. But your question was if I have negative and positive. So in that case, I get 1 here. So that one okay lah. So far, I'm missing here. I don't know why it's gone. There were so many steps. I think I made a drop a bit somewhere.
All right, thank you, sir.
Yeah. Maybe some of you. Okay, let's take a 10-minute break. Maybe I can double check this answer.
Sorry. At the meantime, I have another question.
Yeah.
Let's say this example is like we have one green box, right? Is there any possibility that, let's say we have 2 green box and 1 green box, we always take the first green box only, right?
You understand? Big box.
The green one.
The green one.
He's
Yeah,
talking
because
about
this-
the most significant bit,
the
the
sign
green
bit.
box.
Yeah.
The sign bit. Okay.
So this sign bit is always one only, right? Or we can have 2, 3 more than that.
Normally, this is the okay. You can specify anything, but this is the normal way lah. The normal way of doing it is just keep the fraction only. Even in have you used quarters? Use very low.
Yeah.
If you look at the waveform, you can specify the waveform as binary, hexadecimal, and fractional.
Yes.
You can try fractional in Verilog waveform. It will give you this format also. It will give you 1 sign bit and the rest fraction bit. Same. So not only ARM, also Verilog also does the same thing, same behavior. Okay, 1 bit, 1 sign bit, and the rest is the position of the binary. The binary position, the binary point is always the same.
Oh, so by your meaning is this green box is only one only, it will not be one. Okay, I got your meaning.
Yeah. So that's why when let's say I multiply these 2 numbers, I want to keep the result, right? So I have 0.7 times 0.75. I want to keep the result, which is 0.375. So how do I extract 0.375 from the long answer? Okay, when the multiplier multiply, you get a very long bit pattern. So from that bit pattern, which part of the bit pattern will give you 0.375? That's That's the original question.
Mhm.
The original intention of the slide lah.
Okay. I see this one, the example is like 7 byte, 7 bit, 7 bit lah. So, I mean, let's say 8 bit times 7 bit, do we still using this? I mean, this one is easy to see ma, because we just use back the 7 bit as a reference after, I mean, we refer to 7 bit, but is there any other example? Like the 8 bit times 7 bit, some sort is
Oh no. Normally it's same size lah.
normally same size one lah.
Normally same size. Normally it's 8 bit or 16 bit only.
Oh,
You don't go to
okay.
funny size lah.
Yeah, because I worry about that.
Yeah, no, because the hardware doesn't support also.
Okay, sure. Understood.
Because, okay. If you are anybody of you using TensorFlow doing CNN, anybody, you are going to use. I assure you for the assignment lah. But anybody using? In TensorFlow also, this is the format, same. You're using for AI. So it's the same anyway. And Q7 this is Q7. Okay. The problem is when you start adding integer on the left. That's why we tend to skip the integer lah. That's why this format lah. This format we don't normally find. We don't normally find this. We only use the fraction only. Convert everything to fraction, then everything is fraction, so you don't have to worry about the integer.
Okay, appreciate for the explanation.
Oh, you get me sweaty lah, so take short rest. I have to figure out where I did a mistake when you try this negative. I actually haven't tried negative times. So now I think something. If I want to do this myself in TensorFlow, I also can't do it.